We are excited to welcome our amazing speakers to this event who will be sharing with us their incredible work on STEM projects. We have presenters today, Rajiv, Anwita, Ashvin, Aneeka, and Meera. So to all presenters, please ask to join the stage. It should be a reddish button in the top right corner, which says ask to share audio video, and that will put you in the queue for the presenters. So we can take turns in presenting, and I'll be calling each of you by name so you don't have to remember when you're presenting. But again, Rajiv will be the first one. Rajiv, I can see you. I can see Ashwin as well. What about Anwita, Aneeka, and Meera? Are you here? If you are, please say it in the chat, or if you have trouble joining the stage. I'll also start the chat. Please, everyone, share with us where you are joining us from, the physical location. Got it. So Anwita has some trouble joining. Please find that button in the top right corner, which says ask to share audio and video. Great. So we'll get started in a moment. And I would also like to take a moment to welcome our mentor judge today, Brianna. So Brianna, are you here? Can you join us on the stage for a moment? So all right. So I just share my screen for a moment. So Brianna is a PhD candidate, and she's a third-year PhD student in computational neuroscience at the University of California, San Diego. And she's currently working on biophysically realistic models of seizures following traumatic brain injury and how to prevent them. So we welcome her. Thank you so much for joining us today. And with that, we will get started. And the first talk will be by Rajiv, who is a student in Burlingame High School from Burlingame, California.
All right, cool. Am I muted, or?
We can hear you. Please feel free to share your screen.
Okay. Let's go. Here we go. There we go. Now you can see that, right?
Yeah. Great. So I yield the stage, and please feel free to get started. When there are 2 minutes left, I join with my video on, but microphone off. That's just a signal that you have 2 minutes to wrap up.
Cool. All right. So hi, everyone. My name is Rajiv Koliwad, and my project is about using machine learning to improve how people actually learn. And before I get started, I would just like to thank my mentor, DJ Passy. He's a postdoc at UNC. And he's helped me so much throughout this process. And I'd also like to thank my previous computer science teachers. All right, so you might ask, like, why? This doesn't make much sense. Why use computer science to help improve education? Well, I think it's a very clear application of computer science. So students oftentimes have many different ways that they learn. Some students like to read, and some students like to interact one-on-one with the teacher. And for most students, they can only access that during classes. But when they're outside of classes at home, the only way to do that is using tutors, and they can cost a lot of money. But making a software that can replicate how a tutor or a teacher might interact with the student, it can offer a very low-cost alternative that might be very beneficial and help democratize learning for everyone. So I think it's a really interesting application of computer science. All right, cool. So this is just going over how neural network would work, and so it's actually in this setting, it's very similar to how teachers work and how we already know schooling works. So the input would be how someone did on a set of problems. So that's like if you had a homework assignment or you were doing a worksheet in class, right? You just do some problems and you would then pass it on to step number 2. And the teacher would act as step number 2. And they would go through and they would analyze what you did, and they say, okay, well, you missed problems, 1, 2, and 3. And those problems all have to do with addition. So maybe you're struggling on addition because you missed them, but you got problems 5, 6, and 7 perfectly right, and those are on subtraction. So you probably understand subtraction very well. And then they can use that analysis to go to step number 3, which is a result. They can finally say, okay, you understand addition, or you don't understand subtraction, or whatever they come up to, whatever they learn from analyzing your work, they're able to make a prediction on how well you understand a certain principle, and how well you might do on future problems like that. All right, cool. So this shows how questions can have interdependence. And so you don't have to understand the math, but just know that 2 and 17 are more similar than 3 and 17, right? So if a student gets problem 2 right, they have a higher likelihood of getting 17 right, and we can say that they're related to each other, they have correlation. Same thing if they get 2 wrong, they're probably going to get 17 wrong. But 3, if they get it right, we don't really know how they're going to do on 17. And if they get 3 wrong, we don't know how they're going to do on 17 as well. So there's a more of a correlation between 2 and 17. And so a model can use this and use this format to then get to this step right here. This is a more scientific view, or more accurate view of how the model actually works. But it's still very simple to what we saw here. It's pretty much the same thing. So on the left-hand side, we input how a student did on some problems. They either got them correct, incorrect, and we put that into the model in the middle. And this model we'll get to in a second. But basically, what it does is it takes this student performance on these diagnostic problems, and it'll say the probability of getting these last 3 questions right that highlight ideas that were present in this initial problem set. And in the middle here, that's kind of going over the middle passes on information that it got before. So incorrect problems get passed on, and the fact that it was incorrect gets passed on. But over time, the model will learn what's important and what's not important. So for problem number 1, for example, here, this 90%, even though we got problem 2 wrong and it's passing on red, it's probably the weight, as we call it, is probably very low for problem number 1, because even though it's passing down, that we got it wrong, we're still having a high percentage of getting our probability of getting that one right. But this one, possibly question number 1, is very important for that. And so this weight is very high, and so we still get 90%. Whereas for 11, if we got one, question number 3 wrong, our probability of getting 11 right is very, very low. So maybe 3 and problem number 3 at the end are very correlated. So that's how that would work. And then based off this, the model could see, okay, what the student has to work on, and it could give you more materials, just as a teacher would. All right, so this is our progress so far. So far, we've actually created this neural network, and we validated it using synthetic data. So this exists, but we haven't actually used real data. We've used computer-generated synthetic data. This project has also gotten scientific, has been approved by a scientific review committee at the San Mateo County the Office of Education. We've made our experimental design, and we've actually started some data collection as well. And so in this data collection, we created problems that specifically pinpointed ideas in math that would make that relationships between problems apparent. So the model could actually learn off of performance on the first set of problems to this last set of problems at the end. Get a strong connection between them. Yeah, so we actually have some responses here that we can go look at. So on this y-axis, you'll have how many people put an answer, and on the x-axis, on the x-axis, you'll see the multiple choice answer that they selected. And so this is for all 17 problems, and I just kind of wanted to go in more specifically for question 16 and 11. So 16, the answers are very concentrated at D, right? D is a very popular answer choice. Whereas in 11, people are choosing many different types of answers. So it's interesting how we were able to make problems that either everyone got right, or problems that were slightly more challenging at the same time. So this is a coefficient. This model, or this graph, shows how question and answers are correlated to each other. It's a coefficient correlation matrix, yeah. And what it does is it shows on the y-axis problem responses, on the x-axis problem responses, and it shows how similar the responses are. So this diagonal down the middle basically shows that 1 and 1 are related because they're the same answer. They're going to be exactly the same. But we can see more interestingly that we have some problems like 2. 2 is only related to itself, and like, you know, a little bit related to 10, but everything else has no relation, or very, very, very low correlation to everything else. But a question like, you know, 14 is like pretty good with most of them, but it has a really high connection with 6 and with 3. So even with this little amount of data that we have, we can already start to see these connections bubble up. And it's a really good sign that with these questions, we would be able to make a model that would work, just given, you know, more responses and more time. So yeah, in the future, we would really love to get more data to try and build out this idea further. And we would also like to train the model on we would like to train this model that we've already validated using lab data on real data. And then hopefully this model would be able to, you know, recommend materials to students that would be able to pinpoint specifically what they need. Thank you so much.
Thank you, Rajiv. That's very impressive work and great presentation. And question time from the audience. Please request to join the stage. I'm going to so we have a number of people who have indicated they'd like to join the stage. Brianna, Chinmayi, and some of the other presenters, and Shreya. So if you could just drop your name in, you could indicate in the chat if you want to join, I'll invite you. In the meantime, I have a question. So you showed some data that was, if I understand correctly, synthetic data that you generated, right? So how do you think these results might differ if you had real human data to work with?
Yeah, totally. So the synthetic data is created so that problems will be synthetically correlated. So problem number 3 and problem number 16 will have a very strong correlation. So that correlation coefficient matrix that I showed earlier at the end of my presentation, they would be very high, or they would have very specific, predetermined correlations. That's what you hope for when you get data back. You don't always know that the data will be able to, that you can learn off this data. Sometimes if you go off into the real world, you'll think, oh yeah, these problems are totally related. But in reality, when you get the responses back, they're not. And so having that relationship that a machine can actually, or that a computer can learn off of, is very important. And that's kind of what we're showing at the end, that this is starting already to show those correlations, that the model, it just shows good signs that it'll reflect similarly, it'll work as it did in the synthetic data.
Got it. Thank you, Rajiv. So there is a comment or question in the chat. Rajiv, if you see it, maybe you can comment on that.
Oh yeah, that's my mentor right there. Yeah, so yeah, those histograms that I showed you were from the actual, sorry, I might not have made that clear. Yeah, those were from actual real responses that we got. And so it is showing us that even though we haven't gotten a ton of responses, it's showing good signs for the responses that we've gotten so far, that it should work in a real world application.
Got it. That's great. Any additional questions? We have 1 more minute left. I have an infinite list of questions, but would love to get some others to say more. Brianna, I see that you're requesting to join the stage. Can I invite you? All right, I'll just ask my question. So you mentioned that some of the work you did was approved by a scientific committee. Can you say more about that? Yeah,
so in order to interact with, in order to send out the survey, we wanted to make sure that we were abiding by all the rules. And so I had to, fill out this whole form. I had to make a consent form just to make sure that everyone knew exactly how we were using their data, and make sure that in the future, if we wanted to publish our work, we could actually publish their information, without any identifying information. So yeah, we had to apply for that, and we got accepted.
Great. Let me invite Brianna.
Oh, hello, there we are. Yeah, I think your response to one of the previous questions was kind of getting at this, but you have this kind of one direction of how you're going to use this network. And have you thought about using it in a different way as well to kind of like analyze existing curriculums and build curriculums based off of the results of the network like this?
Oh, that's interesting. Yeah, I haven't actually thought of that. Well, the way that I got this idea was kind of during online school, but also just looking at like massive online courses, right? So like I think they're like MOOCs, for example, right? They have a huge they have a huge amount of responses, and you're able to make that's how most of this learning has done, or most of the scientific community has tried to apply this educational based data. So I think that definitely it could be used. Sorry, I just want to read the question again just to make sure. Analyze and develop curriculum. That's interesting. I think it could. I think it could. I think if you're able to see, if the model is able to see, for example, like Khan Academy, it could say, hey, these problems aren't really a great. These final problems that you have aren't really great predictors. These original problems that you're giving as practice, and the real world problems that they're going to have to apply them in, they aren't very good. They're not very correlated at all. So you might want to change the curriculum to make it more accurate. Yeah, I definitely think it could do that.
Yeah, I think this is a super cool project with lots of potential. So great job.
Thank you.
Thank you, Rajiv. Thank you, Brianna. So obviously there might be additional questions. Feel free to ask them in the chat. But in the interest of time, we'll move on to Anwita's presentation. Anwita, please join us on the stage. I'm inviting you right now.
Hi.
Hi, so we can hear you. Please feel free to share your screen. And I'll just a public service announcement. I'll remove everyone who is not a presenter. But if you want to join the stage, feel free to request it and I'll approve it. But right now, only the remaining presenters have been left here. So if you want to join, just indicate it. Anwita, the stage is all yours.
Are you able to see my screen?
Yes.
Okay, great. Hi, everyone. So my project is on the brain's dance, understanding the neurobiological implications of the brain during Odissi dance. So I'm a high school senior in California, and so my presentation is about neurobiology of classical dance. And so you may be wondering how these two completely different topics are connected. So a quick introduction on me may help you understand a little bit. I've been doing Odissi for about 13 years now, and I have my bachelor's degree in Odissi dance from an Indian university. And I've written numerous analytical and comparative papers about the history and style of Odissi dance, as you can see on the left. But in high school, as a freshman, me on the right, I got really interested in studying the brain. This is me holding a small piglet brain. And this paper is a very interdisciplinary topic, combining both my passions and interests in dance and the brain. So a quick review on the history of Odissi, or what Odissi is in general. Odissi is a traditional temple dance from Odisha, an eastern state in India. It's been traced back to the 2nd century BCE, so one of the oldest living dance forms in India, and there are many different styles. But this paper really focuses on two interrelated topics, bhavas and rasas, which is roughly and loosely translated to emotions and moods created. So bhavas and rasas are very commonly seen in emotional and expressive dance pieces surrounding specific tales or fables. And these dances are highly emotional and typically fixate on one or two major emotions in the dance. Bhavas and rasas are very difficult concepts to execute because they're kind of correlated. You can't really have emotions without moods or moods without emotions. And there are 9 major rasas or emotions: love, laughter, despair, amazement, disgust, courage, fear, anger, and peace, as you can see on the right. Dancers train for years to be able to successfully create bhavas and rasas, and the specific aspect of dance training could be one of the factors that contributes to the differences in a dancer's brain that I really hope to examine in the future. So what has already been said about neuroscience in the past? So Odissi dance, more specifically bhavas and rasas, contribute to a unique model about how the brain develops motor expertise, as well as simultaneously developing emotional creativity and performance. So I'm looking a lot at the neurodevelopment and the neuroplasticity of a dancer's brain. The neuroscience of dance is said to be an emerging field, so on the left, with great applications to neuroplasticity and therapeutic applications. The long-term effect of dancing is a higher levels of neuroplasticity, and it also changes both the gray and white matter of the structure, effectively changing the overall structure of the brain. But Odissi dance is very significant in a way because it also has a lot of emotional training. So a lot of this research, all of this past research, can only be partially applicable. So moving over to the right, where we talk a little bit about the emotion and the brain, the study of the neuroscience of emotions is actually a very vast field. The constructionist approach is often used where they say a lot of different sets of brain regions kind of combine together in creating and maintaining emotions. Moreover, regulation of emotions show that regulatory strategies are different from individual differences in emotional regulation, and both of which are used kind of for emotional control in these dances. So although there's a lot of research about dance in the brain and the emotion in the brain, there's really not much done together about Odissi dance, brain, and emotions together. So my experiment tries to understand how these topics really connect and help us learn about how a dancer's brain may differ from a regular brain, and really help see whether these techniques used in dance can be used for therapeutics for future or past or current disorders like ADHD or bipolar disorder, and etc. So what my experiment actually was. So in order to test the dance, the brain functional levels in dance, I conducted experiments on Odissi dancers all over the Bay Area and Northern California. With their consent, all of this data is from their experiments. The participants were a mix of teachers and advanced students who had more than 5 years of training. So participants were given sets of stimuli after different timings of dances. So the first test was the differential emotion scale that you can see on the left with a 5-point Likert system. So participants were asked, as you can see on the top picture of the left, were asked to rate 30 different emotions from 1 to 5. And the second test was a video test where you can see on the total right section, where the participants were asked to identify 5 black and white faces from a 30-second video from 6 discrete emotions: anger, happiness, sadness, fear, disgust, and surprise. And lastly, the artwork test, which is in the middle, where participants were asked to categorize abstract artwork into the same 6 discrete emotions, and their responses were timed. All of the bottom row for all 3 sets are the analysis for each individual respective test given put there by GraphPad Prism. So first they were given a control stimuli with these 3 tests, and then they danced for a minute and looked at a different set of stimuli, and this process was repeated after 3 minutes and 5 minutes. In GraphPad Prism, I sorted each dataset into many different categories, including style, amount of dance training, type of style, teachers versus students, and all of this really helped understand specific themes or specific conclusions that I came to with my results. So first conclusion I want to talk about is the DES scale test. So this one discusses 2 groupings. On the left, the emotional training, and on the right, the type of dance training. Type of dance, yeah. So for the emotional training on the left, we can see that with more training, the fluctuation of the mental states, mental and emotional states actually decreases and condenses really. As you can see, I don't know if you can see my cursor, but on the bottom right, you can see that they're very fluctuated, but on the top left, they're very centralized. This shows that the training these dancers go through have significant impacts on their mental states by calming or cooling or keeping it stable. And on the right, we can see for the type of dance that non-emotional dances had a lot of fluctuation in emotion states, but the emotional dances were also pretty stable. This shows that techniques used for emotional generation and regulation in these emotional dances are really good for stabilizing disturbed emotional states. Both of these discoveries are especially helpful for patients with like bipolar disorder or emotional dysregulation, borderline personality disorder, ADHD, as this kind of dance training with emotions can maybe help with emotional states and calming the mind. And so my second conclusion was that plasticity is like a bell curve. So these are the video results. And so on the left is the emotional training, and on the right is teachers versus students. Although although video accuracy results in general were decreasing, these 2 had a lot of specific significant results. So in teachers versus students, the teachers tended to have a higher accuracy in recognizing the facial expressions of these pictures in the video. And these teachers typically tended to be part of the 20 plus years in the emotional training on the left. And you can see that the peak accuracy here is actually from 15 to 25 years. So this shows that plasticity works like a bell curve. When you start really young and you go to like 25 years, you gain a lot of plasticity. Your plasticity is increasing because you are gaining experience, and with dance training, it increases. But after a certain year, it actually decreases due to other effects like age or gender or other external factors. And lastly, emotional recognition timing decreases with age. So on the left, you can see a decrease in the response timings for the age artwork as age decreases for emotional training. And this goes to show my last point that actually plasticity decreases with age after a certain point. But on the complete right, you can also see that these exact people with higher timings actually did have a higher percent accuracy. So that's, something that is unnatural, but something that I want to look into further in the future. But while looking at the type of dance training in the middle, we can see that the type of dance actually does not affect the results. So whether you did an emotional dance or not, whether your emotional circuitry was fired or not, actually didn't affect the results. Therefore, the factors that did affect the results might be age or gender or other external factors that I hope to look at in the future. So a lot of my research has a lot of applications for therapeutics, but I would hope to study this in the future, especially if I go to college and have the opportunity. And I want to thank you all for your attention, and special thanks to my mentor, my family, and the participants, and Polygence for giving me this opportunity to study this. Thank you so much.
Thank you very much for the great work you've done and the presentation. Any questions from the audience? And feel free to request to join the stage. So Brianna in the chat is asking a question. Anwita, can you see the question?
Yeah. So what was most surprising to you in my results? I definitely think that the DES scale, where with age, emotional states were really stabilizing. That was really unexpected because I kind of thought the opposite going into it, really that emotional states might be more stabilized when you're younger because you have a lot of more control. But actually it was quite the opposite. And it makes a lot of sense because with training, you do have a lot of control over which emotions you're projecting and which emotions you let control your own emotions, your mental states and stuff like that. Yeah.
Thank you. Any other questions? Anyone else wanting to join the stage to ask their question? So let me just ask you, Anwita, it seems like you've done a lot of work, actual experiments. What was the hardest part of doing this project?
I think it was definitely the experiments. I got to thank my mom for that quite often because we traveled far. We traveled like hours and hours to do the experiments because there were 20 participants who were all around the Bay Area. So oftentimes it was like an hour from my house and we'd come back and then go back an hour. And so I really do have to thank my mom for that, for driving me everywhere. But that was definitely the hardest part because driving and committing to these people's places or their studios was definitely really difficult and also time consuming.
Well, great job doing an actual experiment and going outside the ivory tower of research and talking to people and gathering and doing field work essentially. Yeah. Great. Any last minute questions for Anwita? Great. Well, Anwita will be around and we'll be gathering at the very end of this session all speakers to the stage. So you might have the chance to ask further questions, but Anwita, please connect with everyone who have further questions. And thank you again for your presentation and work. Great. So next up will be Ashvin from Cupertino High School. Ashvin, please join the stage.
All right, can you hear me?
Yes, we can. Please share your screen.
Let me see if I can get it to share the right app because it would share my entire screen, right?
You can also select to share just the tab.
Okay, yeah, I got it.
Got it. Wonderful. Okay, we can see your tab, so the stage is all yours.
All right. So hello, everyone. My project is titled The Economic Indicators of Higher COVID-19 Vaccination Rates and Identifying Strategies to Get More People Vaccinated. So first, before I begin, I'd like to thank my mentor, Evan, who's kind of supported me throughout this entire journey and helped me come up with many of the statistical analyses in order to actually develop my project. So before we actually go into some of the more specific methods and data that I got from my project, I just wanted to kind of go over an abstract that kind of talked about in general what my project was, what are some of the key results that we found, and I guess what potentially that might mean we'll cover a little bit later into this presentation. So in general, I just wanted to kind of find what leads to higher vaccination rates, because throughout the country we've seen a bunch of different vaccination rates, whether that be high vaccination rates in like the Santa Clara County where I'm from, and low vaccination rates in many other countries throughout the nation, or many other counties throughout the nation. So I thought it would be like an important and like pressing issue to maybe find out what is some things that have led to higher vaccination rates, and what are some strategies that we can use to like increase vaccination rates in those areas that don't have as high vaccination rates. So in order to do this, I created a novel data set by compiling data from a bunch of different online sources. I also found a correlation between unemployment and median household income, which I will discuss further in a bit. And then we also had a Wyoming case study where we specifically pulled data from Wyoming in order to like find like a couple differences between a couple of counties and comparing and contrasting some factors between these counties. And then we also ran tweet analysis to see if there was something with the like state health department tweets that could lead to higher vaccination rates. So just as a general background, I'm pretty sure we all know what COVID-19 is. It's the pandemic that's kind of like really impacted all of our lives over this last 1.5 years. It's taken up 40 million cases within the United States, and we've had more than 600,000 deaths due to this virus alone within these past 1.5 years. In order to combat this virus, there are 3 COVID vaccines that have been released: Johnson & Johnson, Moderna, and Pfizer within the United States. There's also been a massive rise in vaccine hesitancy and anti-vaccine sentiment, where many people simply just refuse to take the vaccine. And that is something that we will also be discussing further in depth in a little bit. And also finally, recently, within maybe like the past couple months, we've seen the rise of the Delta variant, which is another variant of the COVID-19 vaccine, or of the COVID-19 virus, which has led to like more cases. It's more contagious and has led to more deaths and more serious illnesses among the unvaccinated population. So in general, with the methods, what we first do is we create a novel data set using data from the CDC and the USDA ERS. So what the CDC data set has is it has like for each county in the United States, it's going to have like how many like people have gotten vaccinated, what percent of people have gotten vaccinated, what's like the general like vaccine hesitancy within these regions, because they have like a metric of calculating that. And then when we look towards the USDA ERS, we have some things like education, we have income, we have unemployment, and we have a bunch of more like economic factors that we're going to be looking towards tying in. And then we also look towards finding correlations. And in order to do that, we use the Python packages of Pandas, Seaborn, sklearn, and SciPy. And then the 2 things that we primarily focus on are unemployment and median household income. We also run OLS regression in order to find which like things are actually significant or not, statistically significant or not. And then we run tweet analysis, and we use Twint in order to actually pull these tweets. And what we're actually going to do is we're going to pull tweets from state health departments in order to compare that to state vaccination rates in order to see if there's a correlation between those. And we only want to pull tweets that have the word COVID as well as vaccine, vaccination, or vaccinated. So we only are going to pull the tweets that are actually related to COVID vaccination. So here's the first results that we kind of have. We basically plotted out all of the vaccination rates from the United States as well as the unemployment rates from the United States on a map. As we see here, we have many geographical like regions that have led to higher vaccination rates and lower vaccination rates. If we look towards the vaccination rate map, we see that the West Coast and the Northeast have higher vaccination rates, while when we look towards the geographic South as well as some of like the central regions of our country, we're going to have lower vaccination rates. The areas with white space are counties for which the data is unavailable. So we don't have data for Idaho, New Mexico, Texas, as well as large parts of South Dakota and Nebraska. And then when we compare this to the unemployment rates things, we see that this is also kind of like largely geographic, when that like in certain regions we see higher vaccination rates and higher unemployment rates, and in certain regions we also see like the opposite of that. So then we also pull the specific like state of Wyoming, because if we look over here, we have this one outlier county which has a greater than 70% vaccination rate, while everywhere else in the state we have less than a 50% vaccination rate. So I wanted to kind of like look at this one county and see if there's something within this county that would lead to like that county having higher vaccination rates. And what I did is I went to their website. On the left, we have the vaccination. We have the website of this county. We have the Teton County website, and on the right, we have the Campbell County website. And the Campbell County is one of those counties that had a below 20% vaccination rate. If we look at the Teton County website, we see that there's very like in-depth information on their website. And on their website, one thing that we can like specifically notice is they have like not only just like vaccine-related information, but information specifically targeting vaccine hesitancy, which has been an effective strategy within the Teton County to increase vaccination rates in comparison to the Campbell County, which only specifically just says like, okay, go get vaccinated if that's what you want to do. And then once we found those results kind of like with the website on the Wyoming case study, we then also looked towards some of like the general data analysis. One thing that was extremely unexpected that we found was a positive correlation between unemployment rates and vaccination rates. We had assumed that like when we have higher vaccination rates, these are probably going to be areas that also have lower unemployment rates like during COVID. However, this proved to not be the case. We have all these places with like, I guess like in April 2021, the places with higher unemployment rates generally did end up having higher vaccination rates. So this was actually extremely unexpected. We did not expect this to happen at all. And what made this even more unexpected was that when we looked towards median household income, we also saw a positive like correlation. So we noticed that like when we have higher incomes, this leads to higher vaccination rates, yet at the same time, higher unemployment rates also lead to higher vaccination rates. So what we kind of generally like concluded was what this means is mostly like places with low unemployment rates as well as low household incomes are less likely to get vaccinated, because if we look at these regions, what we assumed was like within these regions, we're going to have like a lot of people who feel stable with where they are with like a job and everything, even if they don't have as high incomes as other places. While in many places that have like higher unemployment rates, they might feel like a vaccine is a way for them to like rejoin the economy and get back into like the pre-COVID economy, which might have led to higher vaccination rates in those areas. And then we also ran tweet analysis using Twint, and we pulled State Department tweets and compared that with the state vaccination rates. And these are the results that we found. We found a general positive correlation, but it's not as strong of a correlation, which implies that if we're able to look at this in combination with the Wyoming case study, that it's not just tweets or not just information that would lead to higher vaccination rates, but it's specifically positive information or information that actually works towards combating hesitancy that can lead to higher vaccination rates. So as a general conclusion, what we have found was that when we have these economic factors of unemployment rates and median household income, both of those have led to higher vaccination rates when regions within higher, and we need to specifically target regions that have low unemployment rates as well as low median household income rates in the future. Messaging about the vaccine, positive messaging about the vaccine, specifically targeting hesitancy, has proven to be an effective tactic through the Wyoming case study as we look towards the website. And we can also hope to use that in the social media sphere. So for future work, what we kind of decided that what future work would have to look at is kind of solidifying these findings, because a lot of that is preliminary and a lot of it is still theoretical, especially with the Wyoming case study and the fact that messaging on the vaccine can be leading to higher vaccination rates. A lot of that is still theoretical and hasn't been proven by, hard data. So when it comes to future research that's going to be building upon this, we should be looking towards identifying that, as well as finding specific causations for the correlations that we found between unemployment and income, as well as the vaccination data. So thank you so much. And then I will now, be taking questions.
Thank you, Ashvin, for the great presentation and the highly technical work that you shared today in a digestible way. So Brianna is joining the stage to ask a question.
Hi, great talk. I think that was really interesting and really well put together. I had a question about when your initial plots of vaccination rates in each county across the United States and how there was some missing data. And I was wondering if you've thought about why that data might be missing, if you have any intuitions, if you think it might be related in terms of places with really low vaccination rates might not want to publish it, or if you think it's completely random.
Yeah, I think it's definitely related. I don't think it's random at all, because one state that I specifically did look at that didn't have any data at all was Texas. And Texas kind of what they did is they didn't publish anything nationally, and they kind of created their own data set, which was it was really weird, and it wasn't really something that I'd be able to connect to a nationwide data set. So I think what they did is I think they intentionally kind of avoided using the national data set in order to maybe just not publish the vaccination rates that they had. So yeah, so I feel it's not completely random. It's these states have specifically decided for whatever reason, whether that be low vaccination rates, that could be they just don't want to submit to national federal government. But I feel low vaccination rates is one thing that's definitely a probable cause of this, but they just decided that they don't want to publish their data and make it as widely available as some of the other states have.
Okay, great. Thanks.
Any other questions? Sharad asked the question. Can you see it, Ashvin?
Yeah. So I saw the questions about a correlation between vaccination rate and education. So we did find a correlation between vaccination rates and education. This was actually a pretty significant correlation, but we decided to focus on some of like the more economic factors for the actual research paper and the project as well. But what we did notice when we were kind of running our initial tests was that when we look towards counties where when we look at the rate of people within the county, where the rate of people who have a bachelor's degree within the county, like a bachelor's degree or higher, if we compare that with vaccination rates, we're gonna have there was a pretty strong correlation where when we have more people with bachelor degrees, more people who have completed high school, less people who have dropped out of high school, less people who have dropped out of college, that's all going to lead to increased vaccination rates. So we did find a positive correlation between education and vaccination rates as well.
Ashvin, thank you so much. I'm sure there are many more questions. I also have more myself, but we'll ask more questions in the chat, and feel free to reach out to Ashvin, and Ashvin, please welcome further questions. And thank you again.
All right, thank you so much.
So with that, we'll move on to our next speaker, Aneeka, who is a student at Basis Independent High School. Aneeka, please join the stage.
Hi, everyone.
Hi, Aneeka. We can hear you okay.
You can hear me, right?
Please share your screen.
Okay, cool.
Great. We can see your screen, so I yield the stage.
Okay, thank you. Hi, everyone. My name is Aneeka Sawarkar, and today I'm going to be talking about the theory of invisibility cloaking. So a little bit about me. I'm a sophomore who loves to code, cube, and golf. My favorite subjects include math, physics, and computer science. I'm passionate about promoting STEM education in girls. I chose this project because I wanted to expand my knowledge of physics by diving into the realm of invisibility cloaking. So let's talk a little bit about invisibility cloaking. Invisibility cloaking is a scientific theory where objects can be hidden from sight. Invisibility cloaking was scientifically proven by Ulf Leonhardt and John Penry in 2006. To make an object invisible, a cloaking device is placed around it. A cloaking device is made of artificially structured metamaterials, which are composed of metals and plastic. The cloaking device bends the light rays, ensuring that they come in and leave the cloak in the same direction. To understand how invisibility cloaking works, we need to know how vision works and how we can see objects. As shown in Figure 1a, when light rays hit an object, the light rays will reflect back, allowing our eyes to see the object. Therefore, as shown in Figure 1b, to make the object invisible, every light ray needs to bend around the object and not hit our eyes. If we do not see the object has become invisible. What is optical media? To make an object invisible, you can use optical media to bend light. Optical media are transparent materials where each medium has a specific refractive index. The refractive index depends on the speed of the light in that medium. To solve for the refractive index n, we use the equation n equals c over v, where c is the speed of light in a vacuum and v is the speed of light in the medium. The changing refractive indices result in the bending of light. One way to bend light is by using lenses, which are specialized optical devices. The most common example of lenses are glasses. The glasses act as a lens to bend light rays, allowing people to see better. The bending of light is governed by Snell's law when light travels from one medium to another. Snell's law, as shown on the screen, is n1 sine theta 1 equals n2 times sine theta 2, which describes the ratio between the angle of incidence and the angle of refraction. Snell's law governs the path the light ray takes through different materials. While Snell's law governs the path the light ray takes, Fermat's principle governs how the light ray bends when the medium changes gradually. Fermat's principle states that a path taken by a ray between 2 points A and B should take the least amount of time possible. Using Fermat's principles, Professor Ulf Leonhardt and Sir John Penry proposed the usage of cloaking devices to bend light to make an object appear invisible. When a cloaking device is placed around an object, a container is formed around it. Light is an electromagnetic wave, which bends in such a way that it travels around the container. Then light leaves the cloaking device by propagating in the same direction and enters the cloak. The light propagates around the cloak and does not hit the object, therefore making the object invisible. When the object is invisible, we were able to see whatever is hidden behind the object, but not the object itself. Cloaking devices are made of artificially engineered metamaterials, which are composed of circuits. The circuits are made of metals and plastic and produce an electromagnetic field, which makes an optical medium where each layer in that medium has a different refractive index. As stated in Fermat's principle, light rays will bend around the cloak to optimize the time it takes to travel through the medium. To illustrate how invisibility cloaking works, this figure shows a visual animation created in a computational tool called Wolfram Mathematica. The chamber where an object can be invisible to the naked eye is shown within the blue circle. The cloaking device made of metamaterials is shown in the orange area between the green and blue circles. The cloaking device bends the light rays, shown in red, around the cloak, making the object invisible. After a light ray emerges from the cloaking device, it regains its original direction and its path is restored. While a cloaking device can theoretically make an object invisible, it also has some practical and beneficial applications. Similar to light waves, the path of seismic waves can be controlled to minimize or deflect earthquake damage. For example, a hospital can be protected during an earthquake by precisely drilling an array of holes at specific angles and depths around it. As shown in the picture, this could possibly scatter earthquake waves, protecting the hospital. Likewise, in the ocean, an oil rig could be protected against damaging ocean waves by placing a pattern structure on the seafloor to avoid a disaster. I cannot wait to see what we scientists can achieve with the scientific theory of invisibility cloaking. Thank you to my parents for their support and my mentor, Dr. Janusz.
Thank you, Aneeka, for that presentation. And for all the hard work you put into this project. I know this project relatively well, as I was Aneeka's mentor. So I'll readily ask the audience to ask their questions. Any questions for Aneeka? Brianna.
Hi, great talk. So this was super interesting, and I really liked the kind of real-world implications that you brought in at the end. But I was wondering, since when you say invisibility cloaking, it sounds something completely sci-fi. Like, how close do you think we are to seeing some real-world implications of these types of ideas, at least?
So I think the main misconception about this is that, like invisibility cloaking, we talk that it's so sci-fi and it's so not real, and we think Harry Potter and all that. But honestly, I mean, it is a scientific theory, but it's so hard to even try to make that. You need such measurable conditions where you need to be, it's just so hard to do it that I think it would be possible at one point of time, but I'm not sure how close it could be to doing it right now.
Okay, sure. Great, thanks.
Thank you.
Any other questions for Aneeka from the audience? Well, I do have a question, Aneeka, while others are gathering their questions. So some of the work you did here was in 2 dimensions. And so you saw and showed images of light propagating in 2 dimensions. And that's something that would happen with ocean waves as well. Do you see challenges with extending the theory to 3 dimensions?
I think there would be a couple problems if you do it in 3D versus 2D. Obviously, the light waves or the light rays and how they're propagating would have to change our entire simulation animations would change with that. So yeah, I think it would be more of a challenge.
Got it. Thank you for that answer. Any other questions for Aneeka? So then I'll ask one more, which is, what was the hardest part of the project?
Honestly, I think the hardest part of the project would be making the animations in Mathematica. I mean, it's not that easy. It's a new tool that I have learned over the process of a couple years. But, to show how such a complex topic like invisibility cloaking to simple like a simple graphic animation like that. I think that was the hardest part of it.
Got it. Aneeka, thank you so much for your presentation and for your work. If you have further questions for Aneeka, please feel free to ping her in the chat or reach out to her. And yeah, thank you, Aneeka, again.
Yeah, thank you.
So with that, we will move on to our next presenter, Meera. So Meera, please join the stage. Meera. Hi, Meera. Yeah, Meera is a student at Plano East Senior High School from Richardson, Texas. Meera, we can hear you. Please share your screen.
Sorry, I think. I'm clicking the application window and then clicking share, but it is not transmitting, it seems.
So, and are you able to click there should be a little icon of a screen that has a red diagonal line. Are you clicking that?
Yes.
And what?
And then to my presentation window and then clicking share.
Yes. And
But it is not seem to be appearing.
Error message?
No, no error message, just not appearing.
Got it. Are you using Google Slides?
Yes.
Great. So can you drop the link and then I can share my screen?
Yes.
Great. So I am going to share my screen, and Meera, please indicate when I should go to the next slide. Okay?
Mm-hmm.
Got it. All right. Great. So oops. Let me just give me a moment. Can you see Meera's presentation?
Yes, I can see it.
Wonderful. Others can also see it. Please say it in the chat, because this is a somewhat non-standard technological arrangement. Can others comment whether they can see? Yes, wonderful. Okay, so Meera, please get started and just let me know if I should go to the next slide.
Hello, everyone. I'm Meera, and today I will be presenting a review on artificial intelligence and its applications to skin cancer. Next slide. Okay, so recently machine learning has been connected to the detection of a variety of cancers, including breast cancer, lung cancer, and skin cancer. If caught early, skin cancer is easy to treat, but it can also signal the development of other types of cancers, such as colon cancer and breast cancer. Two of the most common types of skin cancer are basal cell carcinoma and squamous cell carcinoma. And as the leading cause of death, cancer often goes unnoticed until late, resulting in drastic tumor growth and expansion. It is even reported that for skin cancer particularly, more than 2 people die every hour. And the early detection of skin cancer could potentially decrease death rates by 90%. With development of technology, particular machines have been developed and algorithms have been developed to work with humans and search for possible tumor growth. Using things like MRIs, magnetic resonance imaging, CT scans, computed tomography, and other techniques, we have been working to search for possible anomalies and using this human and machine analysis to be more efficient and accurate in detection. And the most important overarching subsets of machine learning in this analysis are neural networks, which are a series of algorithms that reach conclusions by mimicking patterns of neurons in the brain, and deep learning methods that is a big machine learning subset with over 3 different types of neural networks. So skin cancer poses a unique difficulty to machine learning algorithms, as tumors can appear anywhere in or on the body, and these cancerous cells can appear in many different forms, which is the value of doing this research. Next slide, please. I cannot see it anymore. I'm not sure if other people.
Let me try and... What about now?
No.
Okay, let me share it again. Can you see it now?
No.
Just give me a moment. Let me stop sharing. So let me share my entire screen. Hopefully that will work better. What about now?
Yes, I can see that.
Great.
Okay, so breast cancer and skin cancer have a variety of understandable differences. However, there is a strong connection between the two cancers that is probably a bit unexpected. A study done on subjects prone to a high number of people that are prone to basal cell carcinomas reported that around 20% of study participants had mutations in genes linked to breast cancer too, including BRCA1 and BRCA2, which, if you know anything about breast cancer, those are typically the ones that are most closely linked to breast cancer detection. Additionally, the study recorded that just under 35% of patients had experienced other forms of cancer, including breast cancer. A direct correlation can be seen here, as related cancer developments have led to over 3 times as many cancer growths compared to the average cancer rate in most senior communities. So now breast cancer has recently become a leading front in the world of AI and medicine, and much energy has been put towards finding efficient ways to process mammograms and interpret them with equal or greater accuracy than radiologists have been able to do so. However, these systems are having limited accuracy largely because of the dense breast tissue that makes up breast cancer. However, these were applied to skin cancer detection because of that connection between breast cancer and skin cancer, and it has taken a slightly different turn. In one study, it was determined that the percent variability between dermatologist skin cancer detection accuracy and AI detection accuracy was only a 7% difference maximum, and AI was generally performing better. Additionally, when similar machine learning algorithms that were highly successful in breast cancer detection were transferred to skin cancer detection, like faster RCNNs, there was higher accuracy rates for detection, often between 80 to 90% when used on skin cancer. So therefore, skin cancer has shown even greater development with simpler machine learning algorithms for cancer detection than are necessary for breast cancer detection. Next slide. So many factors play a role in what makes us human, even just physically. This includes gender, race, and anthropometric features. Playing such a key role in skin cancer development makes it important that detection resources have equal accuracy for everyone. Evidence shows that CAD systems trained with an equal number of male and female X-rays were able to achieve the most accuracy in disease detection. Other training sets that were less diverse performed worse. Although the study did not use specific data for skin cancer machine learning detection materials are often composed of neural networks that perform CAD, indicating that similar results will be present. This highlights the value of scientific diversity within datasets and shows that datasets need to be composed by a diverse range of people and situations in order for AI to perform at its best. Another study reported that simple facial recognition programs had error rates of only 0.8% for light-skinned men, while error rates for dark-skinned women faced 25 to 35% or greater in simple facial recognition. In a connected study, dark-skinned people were used mainly in the testing data set rather than in the training data set. And a dermatologic surgeon then categorized the data using the Fitzpatrick scale of skin tones, which, if you go to the next slide, you can see here, which ranks people from 1 to 6 based on the paleness or darkness of their skin tone. And then go back. and is usually used to analyze the risk of sunburn. So a dermatologic surgeon ranked the testing data on this set to see, okay, where are people typically on the Fitzpatrick scale, and then seeing how that results in accuracy for these algorithms. So 3 commercial facial analysis systems from a variety of tech companies used to analyze the data showed that women consistently, number one, had higher error rates than men, and that darker skinned people had higher error rates than lighter skinned people in simple gender classification, not even skin cancer classification, just gender classification. Anyone with a 4, 5, or 6 on the Fitzpatrick scale had typical error rates of near or greater than 20%, 35%, and greater from there. However, 2 of the 3 systems tested even had error rates of close to 50% for dark-skinned women. For something as basic as gender classification, a near 50% error rate is equivalent to having no background information and merely guessing. Here, both gender and racial biases from machine learning are shown in fairly simple testing. The expectation that these higher error rates will be maintained or even raised as the variations of some of these AI systems are transferred to skin cancer detection on a variety of people is highly valid. The clear difficulty is that these machine learning algorithms need to be diverse. Many people are predisposed to biases because they're trained on primarily light-skinned people, as you can see in this last data set where, at the bottom right-hand corner, where an staining set of 100,000 images, most of it ended up being from white-skinned people, and of course wouldn't perform well on people of darker skin tones. And so if dark-skinned people were added to the experiment, the percentage of lesions recognized would likely be significantly increased. And some lesions may be more correctly labeled as cancerous rather than having false negative and false positive results. So this would really help with reliability and trustworthiness in machine learning. Next slide. Next slide. So this is also a graph that just demonstrates exactly what I talked about, that among these different scales of the Fitzpatrick skin tone, as you go from 3 on the left to 5 on the right, you get progressively higher error rates in detection of different things, including gender and facial recognition and such. Next slide. So AI versus dermatologists, right? Now we have these incredible machines. They can do a lot for us, or should we keep our dermatologists to help us detect skin cancer? With machine learning influence in medicine becoming a reality, a comparison between human detection and deep neural learning detection is necessary. So on the right-hand side, you can see that in one study between AI methods and dermatologist methods, AI did perform better with a specificity of 82.5%, area under the curve of 0.86. Dermatologists, on the other hand, only had a specificity of 71.3% and an area under the curve of 0.79, which demonstrates that clearly AI is performing a bit better. However, although these results present that numerically neural networks perform better than dermatologists, skin cancer detection should not solely rely on machine learning. In many medical situations, a combination of different dermatologists or dermatologists and other resources are used to come to a highly probable conclusion. Similarly, machine learning employs techniques that put an image into a variety of filters before coming to a conclusion. This demonstrates how substantially more accurate results could come from the combination of man and machine in cancer detection and categorization. This philosophy is supported by research that, if you go to the next slide, is represented here. When only dermatologists tried to perform skin cancer classification and detection, they had a proficiency and an accuracy level of about 42.94%. However, when it was done by machine learning algorithms, there was an accuracy of a little over 80%. When both were combined, it rose to the greatest accuracy of 82.95%, demonstrating that rather than pitting AI and dermatologists against each other, the two sources should create individual conclusions first and then confer prior to informing the patient. This will allow for less biased evaluations and would be incredibly beneficial to the development of neural networks to outline the black box contents, so they could be used at a time like this and help dermatologists understand why the neural network may have come to a certain conclusion before the dermatologist arrives at a final decision on what to tell the patient. So next slide. So overall, there are a few areas for growth. We are at a leading front of this AI application into skin cancer detection, and it's been very incredible, the growth that has been seen over the past decade. However, there is areas for growth, as I've exemplified here. First, we have diversity. We need better detection for a variety of races and genders, and this stems from having more diverse sets of data for these machines to be trained on. There needs to be greater accuracy, therefore, by reducing false positives and negatives that will just happen over time by developing stronger systems and systems that can train more sets of data and then replicate those results onto the public. And then we need greater efficiency, so networks that can work, hopefully at some point in the future, alone from dermatologists or only working with one dermatologist to just double check the work and just make sure that we are able to continue receiving these accurate results just in a faster time span, hopefully. So yeah, next slide. Thank you. And special thanks to Polygence and my mentor, actually, Anwita, who helped me with all of the machine learning aspects to this, as it is a new field, and it was a new field for me to delve into. And I'm really passionate about this experiment and the research that I've done. So I'm really thankful to her for her guidance. Any questions?
Great. Well, Meera, thank you so much for the fantastic work you've done and the great presentation you put together. I think we have our first question from Rajiv, nicely articulated in the chat. Please read, and we'd love to hear your answer. And if you could summarize the question for everyone, that would be also helpful.
Okay, so I believe what he's asking is, rather than simply creating a more diverse set of data, would it be better to, or would it be able to just create algorithms that will work on lighter skinned people, algorithms that work on darker skinned people, and train it on the algorithm that's meant for the darker skinned people or for females, just on females, or just on darker skinned people, and the other algorithms just on lighter skinned people? I think that could work. I think it would be wonderful to just diversify the population, because bias stems from human bias, not necessarily machines. A lot of it is because humans are putting in the undiverse data sets, but that would work if you were only testing, if you only, like, say you and said, okay, this training data will range from a scale of 4 to 6, and it will only be tested on people who are 4-6 on the Fitzpatrick scale as well. That could work. However, there could be error when you say, okay, this will be tested on people from, this will be trained on people from 4 to 6, but applied from people to 3 to 6 because you missed 3 somehow. So yes.
Thank you for that answer. Any additional questions from the audience? And feel free to join the stage if you want to ask it live. So Meera, I have a question. So obviously we are making better progress on some fronts like dermatology than on some others, like facial recognition. Do you feel that our general lack of comprehensive progress should hold us back on trusting results on, say, dermatology?
I think that it particularly depends, but as I represented here, for like different fields right now, we are just not at the place in gender and racial, like on a gender and racial standpoint, where I think it is safe to trust like dermatological data from AI, just because the results that I gave you were from facial recognition systems and for gender recognition systems. And so with those already having error rates that just show that they're just guessing, it's difficult to say that, okay, now these could go and see if this tumor is malignant or benign. So I think that we are at a standpoint where a lot of growth, even though a lot of growth has been made, creating these different neural networks and creating these systems is incredibly difficult. And then applying them to the real world and getting people to trust them, right, is very difficult. But I think that we are at a point where they cannot be fully relied on, and that's part of the combination of dermatologists and AI, right? You need dermatologists to back up that data.
Got it.
Yes.
Meera, yeah, one more question from Sharad.
So cost was very expensive, right? AI is a new technology, like cost is very expensive. AI is new technology, so it is going to be costly, which is a big factor we need to be cognizant of. My research wasn't particularly into the costs of AI and how that affects systems because a lot of it is still beginning to be implemented. But I can imagine that once cost does become a more prominent factor as we implement more of these systems into oncology and into the real world, it will be something that we have to be cognizant of as technology is generally expensive. Hopefully it will be, there will be a turnover as AI in technology is more of a one-time cost than some other costs. For example, if you had to go see a dermatologist 10 times to have them keep reviewing your detection and reinforce that you have a malignant tumor, you have a benign tumor, you have no tumor, versus just that machine taking one picture one time and just scanning it and being able to use that to determine. So I think the initial cost would be more expensive. Hopefully there is a turnover to that.
Meera, thank you so much for the hard work and the great presentation, and thank you for being so adaptive when technology didn't come through the way we expected. Great job on all fronts. And with that, I'd like to conclude this presentation, this session. Thank you so much, everyone, for coming, and please continue exploring the wonderful sessions we have in progress right now. The new set of them have started, and please congratulate all our speakers, including Meera and all the others, on the great job they did. So really, Meera, Aneeka, Ashvin, Anwita, and Rajiv, great job. Thank you for sharing what you did today here. Very inspiring work, and keep up the great work, and continue doing great things and inspiring the next generation of learners.
Thank you.
So with that, this session is closed. Please explore the networking session, the other sessions, and have fun along the way. And thank you everyone for coming and supporting our speakers. And if you have any questions, feel free to reach out to our speakers. They will be more than happy to answer all questions. Thank you, everyone. And bye.